Hey everybody, today I want to show you how to use sigma notation and what that means. So sigma notation is this notation here with this sigma, it's a Greek letter S, and it's a way of abbreviating, if you will, a nice sum. If you've got a bunch of things you're adding together with a nice obvious formula, you can summarize that. See what I did there? Using a sigma. And if you had something like this, the way you would read it, you would say the sum of, and then you'd read whatever the formula was here, and then you would say as n goes from 1 to k. And it doesn't have to start at 1. It could stop at anything. So if you wanted to add the first 10 things up, you might say from 1 to 10. You could even go to infinity. So that's a way of writing a infinitely long total. Doesn't have to use the letters n for your variable. You can use whatever you want. Computers tend to use the letter I. So if you're programming, you might recognize a for loop and having an I as your variable in there. But anyway, that's what this means, and let's see that in a couple different examples. So the real benefit in using sigma notation is it allows you to type your totals, that big expression you're trying to add, into a calculator or a computer or something like that. If you're going to use a TI-83 or TI-84 to do it, what you'll need to type is sum of sequence of, and then remember the sequence command from that other video. It required 4 different things. It required the formula, the expression. It required what variable you're going to use, a start value and an end value. And those are the things that you see in sigma, right? The expression is whatever formula exists right here. The variable is whatever variable is chosen here, usually n, sometimes x, on computers I. And then, of course, the start value is this lower limit, and the end value is that upper limit. So here's a specific example. This sum says, what is the sum of n squared minus 3 as n goes from 1 to 4? And the question says to express that in expanded form and then to find the sum. To write it in expanded form means to simply write out what's actually meant by this expression. And so let's do that in a moment. What that means is we're going to put something into this formula. We're going to put in a couple numbers into this formula. We're going to put a 1 and a 2 and a 3 and a 4 into this formula and see what sort of values it gives us. So if we wanted to write this out, we could do this plus, and then a 2, and then a 3, and finally a 4. And, a little bit of arithmetic. We could find this. It's not that big. This is 1 squared minus 3. So 1 squared is 1, minus 3 is a negative 2. This is 2 squared minus 3. So that's 4 minus 3 is 1. And then this term is 9 minus 3, which is a 6. And this term over here is 4 squared. 16 minus 3 is 13. And so if we were to add all those together, the total here would be, what is that, 19, 20, 18, I think. And that wasn't too bad because it was only 4 terms. It could have been a nightmare had it been 40 terms, but that's why we have the ability to also type this into our calculator. So if we wanted to find this using our calculator, we would type sum of sequence of. The expression in this case is n squared minus 3. The variable we would choose to use is n. The start value is 1, and the end value is 4. And so if you were to type this into your calculator, you should get 18. And so let me try that a second. I'll go into the list menu, which is second list, over to ops, actually over to math to find sum. And then second list over to ops to find sequence. And then I'll write x squared or n squared, it doesn't matter. Whatever variable you use though, make sure you use that in the variable section. So I'm actually using x, but it would work. So x squared minus 3, my variable I typed was x, and then I went from 1 to 4. So here's what my calculator looks like, if you want to see that. There. And then, yeah, got an 18. I will suggest sum it in the right way. I might take off the sum at the beginning and that closing parenthesis and just type in sequence to see what sort of numbers I get. Make sure I see a -2 and a 1 and a 6 and a 13 and so forth. That way I'll know that I typed everything in correctly. In this example, now we are adding up a bunch of fractions, and the fraction is 18 over something, and we're going to put in the number 1 for I, and then the number 2, and then 3 and 4, and because it says infinity up here at the top, that means we're never going to stop. We're just going to keep going and keep going and keep going, and as weird as that sounds, we actually can get a total out of all that. And so let's see what that would give us. So if we put in a 1 for I, that means we have 18 over 100, that's going to be 10 raised to the 2 times 1, which is 2, yeah, 18 over 100. If I put in a 2 for I, then 2 times 2 is 4, and so the bottom is 10 to the 4th, which is 10,000. So 18 over 10,000. The next thing I'll put in is a 3 for I, which would make that 10 to the 6th on the bottom, which is 100,000. Now I'm getting in the way, huh? And so on, and so on. I can't literally write them all out, but that would be what was meant by it. Now, this might seem like how in the world can you add all these things and keep going and never stop? But if we look at each of these, 18 over 100 is 0.18, and 18 over 10,000 is 0.0018, and 18 over 10,000 is 0.000018, and if we were to keep going forever, this is the decimal, 0.1818181818, and so on. It's the repeating decimal, 0.18. Which I believe as a fraction is 2/9 or 2/11. I can't quite remember that. You could type it into a calculator and hit convert to fraction if you wanted to, but I think it's 2/11. Anyway, that's that. So here's an opportunity for you to try. See if you can write out what's meant by this, and then type it into your calculator and see if you can find the grand total. I'd encourage you to hit pause a second and see if you can do that on your own, and then I'll show you what I got. So what was meant by this is to put a 3 in for I, and then a 4, and then a 5, and then a 6, and stop when you get up to 10. And so that produced a series of about 8 fractions, I think. And when you add up those 8 fractions, you get a number that's about 8.694. If you wanted to get that in one expression on your calculator, you could type sum of sequence of and type the formula. And then the variable was I, and it went from 3 to 10. Be careful that you use the capital letter I if you're using a calculator and not the lowercase I, or it will give you an error because it'll think that's the complex number I. Alternatively, you could do that in 2 steps. If you do the sequence first, and then you can actually see all those numbers, and then you can do sum of answer, and it will find the total for you there. Now I'd like to see if we can do this in reverse. Suppose we have some sort of total and we'd like to express it using sigma notation. And so to do that, what we need is a formula for the nth term. And so if I look at these numbers, the first number is 3, the second number is 6, the third number is 9. This is just whatever n is times 3, right? 3 times 4 is 12, and so the last number here must be 3 times 15. And so if I wanted to express that using sigma, my formula in this case is simply take n and multiply it by 3. And now the index here, I chose to use the letter n, and I need to say what n's are required to get my first and last numbers. Well, I started thinking with n equals 1. And the last number in here would be a 15. If n is 15, that would give me the 45 that I want. And so this expression gives me this list of numbers. If I wanted to add up the first 10 triangular numbers, formula for the triangular numbers is given here. Why don't you see if you can write that a moment. pause it, catch me in just a second. So I hope you came up with the sum as n goes from 1 to 10, because I want the first 10 numbers, of 1/2 times n plus 1. Our last expression here is an infinite sum because it goes on forever here. And so we can start by trying to write an expression for each of these. This looks like the numerator is always 1, and the denominator is just whatever term we're on, squared. And so we can write 1 over n squared for our formula. And then for the indices, I started thinking with n equals 1. And to indicate that I want this to go on forever and never stop, I would put an infinity up on the top. So now that we have an expression for it, let's see if you can find the total. See if you can type it into your calculator, and go ahead and hit pause and come back in a second after you've given it a go. So I hope you thought to type 1 over n squared and go as n goes from 1 to but then probably got into a problem here, right? Because how do you type infinity into your calculator? You can't, but you don't necessarily need to. If you just went far enough, a big number, like maybe 100, if you were to type this into your calculator or to type in 200, you'll probably see very little difference. We'll get into why later on in this unit when we start talking about sums and why they converge and how they converge. But the fact is, if you add up the first 100 terms, the next term is so small it barely changes the total. So after typing all that in, I got this decimal on my calculator. And if you put in, say, 300 instead of 200, the decimal number hasn't really changed much. It's now 1.64 instead of 1.63. And if you go out to 500, which is as big as I could go without my calculator giving me an error, it gave me 1.66. And yeah, that's kind of interesting. If you actually go to infinity, you get a kind of an interesting result. You end up with this value, pi squared divided by 6. And so the fact that this weird formula happens to have pi squared over 6 as a result is kind of remarkable. But anyway, that's an introduction to sigma notation, and I hope you can use it well in the future. Let me know if you have any questions, and I'll be glad